Okay. Yeah, thanks for the invitation. It's a pleasure to be here. So I will give this talk on permissionless blockchains from physical resources. Or I think I might have changed the title last minute. This talk is based on two very recent papers. One is called Nakamoto Consensus for Multiple Resources, which is about to appear at the next AFT conference. And the other one is on insecurity of proof of space based along the chain protocols. I'm going to mostly talk about the first one. Both of the papers are with my PhD students, Ahad Baik and Krzysztof Günther. And let me just give a one-sentence summary of those papers, and I hope that during the talk it will become more clear what this is about. So this talk is actually really about blockchains, about really consensus, very back to the roots, not like the snarky, fancy topics that you've heard of in the rest of this morning. So the first paper is basically characterization of Nakamoto-like blockchains, and I will explain all the green terms later, in the fully permissionless setting from physical resources that are secure in the sense of withstanding double spending attacks. And let me give one little spoiler. As a corollary of this result, we will show that we cannot use space alone to get a Nakamoto-like blockchain. So this is where the second paper comes in, where we kind of look at the broader setting, where we don't just look at Nakamoto-like blockchains, but all permissionless blockchains, and we ask if we can get a secure blockchain using space alone. And again, the answer is going to be very strongly negative. Now, maybe there are some experts here, and you will say, but wait, Bitcoin is based on proofs of work, on the majority of the hashing power being controlled by honest parties. And you might also know that there are some protocols like Filecoin, maybe you've heard of the Chia network, or the academic proposal that is called SpaceMint, which replace work with space and have some kind of security claims and proofs. So how does what I just said, compile with those things? And actually, for all three protocols, Filecoin, Chia, and SpaceMint, overcome this impossibility result in a very interesting and different ways. And maybe in some sense, this is a justification why the protocols are like they are. In particular, Filecoin is not fully permissionless. It works in a setting that is called dynamic availability. I will tell you more about this later. The Chia network, which is like a project that I'm involved with, it's also a blockchain based on proofs of space, but not just proofs of space, but also space and time. And I will tell you later what that means. And finally, SpaceMint, which was an academic proposal. It was never really implemented. It is based on only space, but it's not secure in the sense that we would like it to have. It's not sufficient that the honest parties have the majority of the resource at all the time. We need some additional constraints, for example, that the resource only goes up and things like that. Okay. So let me just define a few of the terms that you've seen before on this summary. So the first is the degree of permissionlessness. I use this term fully permissionless, and when I say fully permissionless, this is basically what protocols like Bitcoin and also like the Chia network that I will tell you later do. And this means simply it's a protocol where the consensus, I talk about consensus, right? The consensus is based on the consensus does not have to know who is participating in the protocol at all. So if you think about Bitcoin, you have these miners, and the miner doesn't even have to speak up. They can participate in trying to find these proofs of work and extending the protocol, but they only have to speak up actually when they actually find the proof and actually can extend the blockchain. But the protocol does not have to know who is participating or not. And then there is this classification here is actually from a recent paper by Louis Pye and Roughgarden. Then there are several levels of permissionlessness that you can define. At the very bottom with the completely permissioned protocols where you know exactly which, the set of participants that have to be there. And then there are these things in the middle, like dynamically available. It's basically permissionless, but you have a set of, the protocol knows a list of potential parties that could be there. And the participants have to come from this restricted list. And the even stronger requirement would be quasi-permissionless, which means actually most of the people from that restricted list actually have to participate to get secure protocols. It will be, for example, Algorand or Filecoin. Okay. So I assume everyone in this room knows about Bitcoin. I will just recap a few points that I will need to kind of bring back to your memory for the rest of this talk. First of all, Bitcoin is fully permissionless, as I just explained. And it works in the following ways. So it's a blockchain. It's a sequence of blocks. And to get security, as I'll explain in the next slide, it's made intentionally difficult to add blocks. In order to add a block, you have to kind of invest a lot of resources. You have to solve these proofs of work. And whenever you solve a proof of work, you're allowed to add a block. And it uses something that's called the heaviest chain rule. So in the case, So it is a hash chain, so you cannot kind of bring two blocks together to come into block, but you still can fork. If you have a block, you can extend it in many different ways. So you can see forks like shown here, like a blue fork and a green fork. And the Bitcoin protocol simply specifies that whenever you see such a fork, you should take the heaviest chain, consider the heaviest chain as the honest one. In Bitcoin, the heaviest chain basically just means the longest chain, but in principle, you should take the chain which in some sense needed the most resources to be constructed. Okay, so what's the rationale of this design? Let me also assume that you are aware of this, but let me also recap it very shortly. The goal of making adding blocks very difficult and this heaviest chain rule is to basically prevent double spending attacks. So if I have a transaction and I would like to record it on the blockchain, maybe I sold my bike, I'm getting whatever 0.01 bitcoins for it or something like that. There's this transaction. I receive this transaction from somebody. I let it out in the network. I wait till it's added into a Bitcoin block, and I'm happy, right? Because now it's recorded. I have those coins. Now what could happen is exactly what I said before. There could be a fork. And maybe the party and a fork. And this fork could contain a transaction which takes the coins that previously went to me and spends it to another address. So I cannot add my transaction back to the chain. So these coins go to a different address, and maybe the attacker actually managed to put even a block on top of that. And now everyone considers this red chain to be the honest chain, or not the honest chain, but like the chain that they should follow up with. And my coins are gone, and my bike is gone, and I'm very unhappy. So what Bitcoin does is it first of all puts out an assumption. It assumes that the honest parties at every point during the protocol control a significant majority of the hashing power. So they can solve proofs of space in expectation faster than the adversary. And then if you have this, you kind of are basically safe against double spending attacks. Now, Bitcoin has like this probabilistic nature, even if the adversary has less hashing power than the honest guys, he might still be lucky and find a few blocks faster than the honest guys. So it basically, wait for enough blocks. Bitcoin specifies 6 or more blocks. And if you see like here, and if you see it like, okay, 6 blocks on top of your transaction, you can generally be, safe that this is going to stay there forever. And I think that so far has been no false negatives, and no double spending on Bitcoin have been recorded. So how does this proof of work actually? And so it's a particularly simple protocol. So proofs of work themselves are actually very old. They go back to a paper from Dworkin from the early 90s. The original motivation was to have some kind of mechanism to prevent spams. The idea was whenever I send out the email to somebody who does not have my address in their whitelist or something, I have to add a proof of work to show that I put a little bit of effort, whatever, 10 seconds on a standard CPU into that email, which is not going to be a burden for honest people who send a few emails per day. But if I'm a spammer and I send out billions of emails per day, that's not going to fly. So it's going to make it harder for me. But these proofs of work were mostly under the radar, of course, until Nakamoto came with Bitcoin and used it in their consensus protocol. And the particular proof of work used in Bitcoin is very simple. It goes as follows. I show it here as an interactive protocol between the verifier and the prover. In practice, the verifier is going to be the blockchain. The blockchain is going to create a challenge, which is going to be the hash of the previous block. So it sends a challenge. There is a difficulty, which the protocol specifies, so that blocks arrive roughly 10 minutes, whatever. So there's this difficulty. It goes out to the prover, which is every miner in practice. And then those miners, they hash like monkeys. They try super fast to find some proof. And what is a proof? A proof is simply a nonce, pi, such that the hash of the challenge with the nonce pi is below the difficulty. Say the difficulty is 2 to the 70, then your hash has to start with 70 zeros. And there is a very simple analysis. If we believe that the hash function, which in practice is SHA-256, I think, but if this hash function behaves like a random function, then dequeries are going to be necessary and also sufficient in expectation to find such a proof of work. So this is one resource that we can think of. This was work, or parallel computation or hashing power. The proof system to show that you invest this resource is called the proof of work. As I just said, the unit here is going to be hashes per second. But I'm going to talk a little bit about different resources too. And for this talk, actually, I'm going to want to consider 3 resources. Apart from work, also space. So the resource here is going to be disk space. The unit is going to just be bits, and the proof system to show that you waste disk space is going to be called proof of space, and I will tell you a little bit about this in a minute. And finally, there's a third resource, which I'm going to call velocity, which is sequential computation. So here the resource is going to be basically the speed at which you can perform a particular sequential computation. The proof system is going to be called verifiable delay function, and here the unit of the resource is going to be called, basically the number of steps you can do per second. And I will do on space and velocity. I will tell you more about this in the next 5 minutes. So proof of space, So this is a proof system that we introduced back in 2015, a decade ago, when Bitcoin was using the electricity of a power plant. Today it's like a mid-sized country. But already then it was kind of clear that, that maybe using the assumption that honest parties have to constantly waste more, more computing power, in particular more electricity, than the potential adversaries, maybe not sustainable in the long run. So we thought, what other resource could we use to implement the Nakamoto-like consensus protocol? And, the first thing that should come to mind if you ask this question is maybe space. If you had the computational complexity course at your university, you maybe remember that after time-space is kind of the next resource that is being analyzed typically. Now, it's not totally obvious how you would generalize proofs of work to proofs of space. In some sense, space is something because you will somehow want to specify that somebody has some space for some time, right? So the protocol we came up with works as follows. It actually has two modes. So first of all, again, I show it as an interactive protocol. First, there is the initialization phase. So there is a prover. It has a disk, let's say a terabyte. And in an initial phase, this prover has to actually initialize this disk. So this is somewhat expensive. The running time is at least linear in the size of the disk because he has to overwrite this disk. But then once he did that, he will send short commitment to the verifier, and that was the initialization phase, and it's only run once forever. Then it's done. Then there is a second protocol run, which is called the proof. So which are proofs, and those proofs can be run very frequently. And in fact, in a blockchain setting, they will be run quite frequently, every few minutes or hours or something like that. And here, the verifier will simply send a short challenge to the prover, and the prover now can generate the proof of, that's what's called the proof of space, extremely fast, typically just accessing a constant number or so of locations of the disk and compiling this proof and sending it back to the verifier who can then verify this proof. And basically, the security property, which I will not go into detail here, basically just asks the following. If the prover does not dedicate almost a terabyte of disk for this proof system, whenever he gets a challenge, answering it will be very hard for him. In particular, it will be almost as hard as reinitializing the entire space. So that's kind of the ideal setting that you would want. And looking ahead, in a blockchain setting where challenges come rather frequently, it will simply not be rational to kind of initialize the space, get the challenge answer, delete everything, reinitialize it, and so on. So it will be rational for a prover to kind of keep that space around all the time, assuming that challenges come sufficiently frequently. There is one problem with this proof of space, as I just showed you. If we want to get the really permissionless blockchain later, and this is this little commitment phi that the prover had to send to the verifier as the initial message. So the original proof that was based on combinatorial structures like this depth-robust graphs and so on really needed this commitment. We had another 2 years later for the Chia network. Actually, we came up with another proof of space which does not have this commitment. So actually here now the prover really, without talking to anybody, he will just basically pick his identifier, which is going to be the public key of a signature scheme, so that he can later claim coins and so on. And using this public key, he can locally initialize his space, and then he can participate in the mining process. Whenever he gets a challenge, he can create the proof. No commitment or anything required to check that this protocol is really secure. Okay, so this was the first new resource that I wanted to tell you about, space. Then let me come to the other resource, which is a verifiable delay function. So a verifiable delay function, it actually doesn't come out of nothing, though. There is this research area that is called time cryptography. It started in '96 with Rivers, Chamir, and Wagner, who introduced time lock puzzles, which was basically encrypting messages to the future. Then we had something that was called proofs of sequential work, which was basically a proof system where you could prove that you did some inherently sequential computation. It wasn't good enough for blockchain applications because we didn't have this uniqueness property. We wanted the proof of sequential computation where at the end you have like a unique value which you then can use as a challenge for the next block and so on. So anyway, so a verifiable delay function as defined in this way by Bonnet, Büns, and Fish in 2019 is, the name is very descriptive, verifiable delay function, is a mapping. It takes some input x, some time parameter t, and it outputs some output y together with the proof pi. And it has the following properties. First of all, it's a function, which means the output y is a deterministic function of x and t. Then it's verifiable, which means that this proof pi really certifies that y has been correctly computed. So this is the unique output of this thing. And it's a delay function, and by this I mean the following. To compute y from x and t, you have to make t sequential computations of a particular kind. And the security property basically requires that, you also need t sequential computation. So even if you have massive parallelism, you have 1 billion cores, you still will need t sequential steps or almost t sequential steps to come up with the output y and the proof. Now, the original constructions of Bonnet et al. Used very general tools. It used the general incremental verifiable computation. So you had like some simple computation that was going on forward, and then you needed like massive GPUs to compute the snark showing that the value has been correctly computed. But then, you know, concurrently, and also even in the same year, 2019, so Benjamin Wesolowski and myself, we came up with a very practical VDF. Both VDFs have the same sequential function, which is basically squaring in groups of unknown order. Not important what that means. Basically, you compute given x and t, you compute x to the 2 to the t, modulo n, where n is some RSA modulus, for example. And these two proof systems basically just differ in how you compute the pi, how you compute the proof that you correctly computed this value. And yeah, and here computing the proof in both of those systems is much more efficient than actually computing the value y. Okay, now that I've introduced these three resources, I will only talk in this talk about workspace and this velocity. Let me classify them along a few dimensions, which will be kind of interesting to understand, so that I can later make more general theorem statements. So first of all, I want to have the notion of a quantitative resource. So a quantitative resource is basically a resource like work or space, or the quantitative resources, which basically means if you give me, if I copy it, I have some kind of whatever. I have twice as much of it, I also have twice as much of the resource, right? So that's kind of what you typically would think of a resource. Another type of resource is going to be a quantitative resource like velocity. Here, remember, the velocity was, I have some kind of particular VDF, and my VDF can do a particular number of sequential steps per second. So you have like a very fast ASIC that does 1,000,000 steps per second, sequential steps. And here, the resource I have, if I double it, I'm not going to have twice as much, because now I have two VDFs which both do 1,000,000 steps per second, but it's exactly the same as before, right? So it's kind of, this is more like, VDFs are more like a technological resource. If I want to have more of it, I have to invest into the technology development. So somehow the quantitative resources are going to be the actual resource, and the VDF, as we will see later, is just going to be necessary to make things work, but it's not really a resource in that sense. And I will also call work and velocity timed resources, simply because the unit of both resources is something per second, right? Hashes per second or sequential steps per second. Okay, so remember these terms: timed resource, quantitative resource, and qualitative resource. Now, I showed you, space and VDFs. So let me tell you a few words about, what was the motivation for this work. So I'm involved with a project that's called the Chia network. It's a blockchain from proofs of space and time. So this notion has been, so this general idea of combining some kind of proof of space with some kind of proof of time to get a Nakamoto-like blockchain has been put forward by Bram Cohen back, a decade ago. So Bram Cohen is the guy who invented BitTorrent as a student dropout, and now this Chia network is his current project. So he's the CEO of the company. And the general idea is the following. Let me remind you that in Bitcoin, for security, we have to make an assumption about the resources. Namely, we have to assume that the honest hash rate at any point dominates the adversarial hash rate. And in Chia, we replace this statement, or the idea is to replace this statement with saying, at any point in time, the space, disk space controlled by the honest parties, multiplied with the speed of the fastest VDF one of the honest parties controls, dominates the adversarial space multiplied with the VDF speed the adversary has. So maybe even if the adversary has a VDF that is twice as fast as the honest ones, as long as he doesn't have at least 50% of the space, we want to be secure. Okay, secure against double spending. So this is just a screenshot from, from the explanation of Chia. You see, it's much more complicated than Bitcoin, which really just has blocks that refer, you hashed it, you get the challenge for the next proof of space. It has like 3 VDFs running in parallel that generate somehow the challenges for the proofs of space that then somehow are infused in this chain. But it's really not important. The only thing I want to highlight is that basically what this chain does is, if you think about Bitcoin, what does Bitcoin do? From my perspective, what I want to think of is Bitcoin basically records the amount of work that went into creating it, right, through these proofs of space. And this Chia thing, this complicated construction here, what it does is, apart from the actual payload and transaction, it records the amount of space and the number of VDF steps that were available for creating it. So it's kind of like a snapshot, recording these things. So I want to have like a more abstract model for these Nakamoto-like blockchains from physical resources. And okay, let me outline this in the next few minutes. So what I think of is I have some parties, let's say the honest parties, there is some clock time, so the world time, the actual time, and at each point in time, the parties have some amount of resources. So, for example, they have like this red curve shows how much hashing power they have over time. The orange line shows the VDF speed. You know, maybe at some point there was actually new ASIC, so that the speed went up, and then the space in blue. Now, what I want to think of a blockchain is a blockchain simply records those resources. Maybe not all of them. In Bitcoin, you would only record the work. In Chia, you would record the space and the speed. But you know, it records the relevant resources. Yeah. And then, if this blockchain was honestly constructed, so that this was the honest parties, I can look at this blockchain and extract the resources again. So I will call this original resources that the parties have in the physical real world. This is going to be the resource profile. And the thing that was actually recorded on chain, I will call the chain profile. Now, if everyone behaves honestly, the chain profile should be basically the same as the resource profile. And I will, for the sake of this talk, I will actually assume that it's exactly the same. And this is actually how these profiles look in practice. So this is, you know, the orange curve is the Bitcoin hash rate. So that's how the work. So this is the information extracted from the blockchain on how much hashing power went into creating the chain. And it's a very good approximation of the actual amount of hashing power. And the green curve on the bottom shows the space that went into creating the Chia blockchain. I didn't find a chart for the VDF speed so far, but yeah, nobody did. Okay. So this is just what I mentioned before. For the sake of this talk, I will assume that the chain perfectly records the resource profile. Okay. Okay. So now I will come to the first important definition for this talk that I will use, and it's called the weight function. And the weight function basically is a function that looks at resources and maps them to some weight. Now, you've never thought about this in the Bitcoin context of that, because in Bitcoin, the weight function is the identity function. It simply looks at the amount of hashing power that went into creating the chain, and it assigns a weight to it, which is basically the amount of work. So a more interesting weight function would be maybe the one that we use in the Chia network. Here we record the space and the VDF speed, and then we say the weight at any point in time of the chain is the product of those two. That's how it's defined. Right? The blockchain defines the weight function. And now that we have a weight function, I can also give you an abstract definition of a chain weight. So assume we have this blockchain, which somehow records some resources. I extract the chain profile out of this blockchain, and then I simply sum this weights up. And the weight recorded in this green part of the blockchain would then be simply what I just said. I sum up the weights of each block, and that's going to be the weight of that part of the chain. Now that I've defined the weight of a part of a chain, I can give you an abstract definition of this heaviest chain selection rule used in Bitcoin. So here, whenever I see a fork, like here the green and the red one, I will extract the chain profile, I will compute the weight of those two profiles, and then I will say, then we will simply consider blockchains, which say whenever I'm in this situation, I will choose the blockchain that has higher weight. So far, everything I told you is an abstract view on Bitcoin or Chia or this kind of Nakamoto-like blockchains from physical resources. Okay, having defined this, yes?
So is it clear that with this definition of heaviest chain selection, like you get exactly the longest chain for the Bitcoin rule? Like the longest chain?
I mean, Bitcoin actually specifies you should take the heaviest chain, not the longest one. Just in Bitcoin, the difficulty is only recalibrated every 2 weeks. So if you're not kind of jumping over an epoch, the weight and the length is actually the same, and it rarely happens that you have longer. So I'm not sure if it ever happened in Bitcoin that the longest chain wasn't also the heaviest. I think you would need very long chains to but in general, okay. Okay, now that I've defined this abstract model, now you should ask yourself, okay, so there is Bitcoin and there is Chia. I showed you these two weight functions. Both of the constructions, Bitcoin and Chia, come with a security proof showing that assuming the honest parties have a majority of the resources at any point in time, double spending is not possible. And now, of course, you can ask the general question. Which weight functions do have these properties? I will say that the weight function is secure. A weight function which maps some kind of resources to some kind of weight is secure if the following is true. If whenever in the real world the honest resources dominate the adversarial resources, I get a blockchain where double spending is not possible. Right? And the question I will want to answer you in the next 10 minutes is what are the conditions on this function gamma to be secure? But before we do that, I want to do like a test your intuition type thing, because I did this before, And people are usually worse than random guessing. So, you know, I think this will kind of give you the justification that this classification actually is interesting. So let's consider, so here I showed number 1 and 2 are actually, number 1 is the weight function for Bitcoin. The weight is, the weight is basically just the work recorded. The second one, space times velocity, is the Chia weight function, which I already spoiled, is secure. Let's hope this. Now, first question. Let's assume I have a blockchain which records these 3 resources, and the weight is simply the sum of the Chia weight function and the Bitcoin weight function. So work plus space times velocity. Who thinks this is secure? And secure, this definition. So, you know, when I use this weight function, whenever the honest parties have more resources than the adversary, there is no double spending. So who thinks this is secure? Who thinks it's not secure? Okay, this is actually secure. Let's take another one. Let's take Chia, but instead of the timed resource velocity, we replace it with the timed resource work. Who thinks this is secure? Who thinks it's insecure? It's actually secure. So, like, you know, everyone who did raise the hand was wrong. In fact, just velocity as a weight function. Who thinks this is secure? Who thinks it's insecure? It's secure. It's stupid because there is no quantitative resource, right? But if the honest parties always have a faster VDF than the adversary, there is a very simple blockchain, right? It's simply whatever chain has the most VDF steps recorded in it, that's a chain, that's secure, right? So this shows that being secure is not the same as being interesting in any sense, right? So I can do that later. Let's say work, you know, let's take again Chia, but replace the quantitative resource space with work. Who thinks this is secure? Who thinks it's insecure? Yeah, it's indeed insecure. Let's take the square root of this. Who thinks this is secure? Who thinks it's insecure? So actually, this is secure. The former one was not secure. So you have to take the square root for reasons that will become secure later. Let's take Chia, but take the square root of the space, not the space when you record it. Who thinks this is secure? Who thinks it's insecure? It's actually secure. So again, everyone who raised the hand was wrong. Let's, instead of the square root, let's take the square. Who thinks this is secure? Who thinks it's insecure? Again, this is insecure. So square root is insecure. Square root is secure. Taking the square is insecure. So before I give you the theorem what secure gammas are, I have to specify what can an adversary actually do when they cheat, right? So what can they do? Because the goal of the adversary should be they have some resource profile, and they want to create a chain profile from that somehow has more weight than if they would behave honestly. So the most important thing they can do is actually lie about the timestamps. And I call this squash and squeeze. Because let's assume on top we have like the resource profile of the honest parties. If they, you know, at the bottom we have the chain profile, that's what happens for the honest parties. Like the chain profile and the resource profile are going to be the same thing. What an adversary can do is, so this, you know, we look at a period of 4 days. The adversary can maybe, he wants to do a fork of length 4 days. In the first day, he creates a chain that pretends to be 2 days. So basically, he just puts in the wrong timestamp to kind of pretend that time runs twice as fast as it actually does. And then in the remaining 3 days, he does the chain for the remaining 2 days. So basically what he does, he squeezes his resources from day 1 into 2 days and squashes the resources from the last 3 days into 2 days. What happens what happens with the recorded chain profile as compared with the resource profile? So what happened here, the difference is just between timed resources and non-timed resources. Because what happens with the timed resources, if I have some kind of, imagine Bitcoin, right? In Bitcoin, I have some kind of resources, I can create a block every 10 minutes. But now I want to pretend, I lie about the timestamp and actually pretend that I can make a block every 5 minutes. So what happens is, I will only be able to do timestamps for half the time that I could do in the honest, behave honestly. Because I'm not suddenly having more resources. So I can squash the time in both directions, but then also the resource will go in the other direction. Whereas with space, this doesn't happen. So if I lie about my space now, whatever I currently have as a resource thing, this will be exactly one-to-one represented on the chain profile. So in particular, this squashing and squeezing will not increase if you look at the weight. If you just integrate over the entire weight recorded, squashing and squeezing will not change the time resources, but it will change the space. Okay. In particular, so there is like an extreme case. Consider a blockchain which only uses space. In this case, there is something that's called generally referred to as bootstrapping. So if at some point in time I have a lot of space, tomorrow I rent like 100 petabyte from, I don't know, Amazon Azure. And now actually with this, in this one day, I can just bootstrap back because creating proofs of space is so efficient once the space is initialized. I can just create a fork that pretends that I had this 100 petabytes for a month if I wanted to. This is called bootstrapping. So this is the extreme case when you have no timed resources. And there actually is another type of attack that you can do with space, which is called replotting. Here, this was as follows. Assume I have like a petabyte space, and I want to create a chain that looks as if I had 3 petabytes. So I can actually do it. So I can initialize my space. I create a block, I record the space somehow, create the proofs of space for a block that looks as if it had 1 petabyte. But then I delete everything and reinitialize it again. That might take some time. And now I use that space to kind of still add to the same block, right? Because these things just add up. So in a lot of time, having this 1 petabyte, after a lot of time, I can actually create a block that looks as if it had much more space. This takes a lot of time. It takes very much time to just get a block that looks as if it had more, depending on how much replotting takes. But it's possible. Okay. So I'm going to very fast through some examples. So here is the Bitcoin thing. So I have 4 days, 2 amounts of resources. I squash it into 2 days. The weight of the chain doesn't change. Here is Chia. I have 1 unit of speed, 2 units of space for 4 days. I squash it. Again, it doesn't change. That's the example that I showed you before that wasn't secure, work times velocity, because if I squash it into 1 day, actually both of the resources go up by a factor of 2, and their product goes up by a factor of 4. Right? So that's it. That's the reason why it doesn't work. Whereas if I had taken the square root of the 2 things, yeah, both of them go up by a factor of square root 2, and the square root 2 times square root 2 is 2, so exactly, I get exactly the same the weight profile as before. Okay, and here's the theorem. So this is the main part of the talk. Here's the complete classification of weight functions which are secure in the sense that I mentioned you before, based on 3 resources. So first of all, they have to be non-decreasing. So whenever some resource goes up, the weight shouldn't go down, because then there are trivial attacks. It has to go at the function has to grow at most linearly in S. So if I double the space, it should not go up by more than a factor of 2. And this has to do with this replotting attacks. I don't want to go into, because otherwise you could do replotting attack to attack it. And the most important one is this one. The weight function has to be homogeneous of degree 1 in the timed resources, which means that whenever I multiply each of my timed resources, velocity and work, with some factor alpha, let's say 2, the entire weight must go up by a factor 2. Okay, that's the classification. So for example, as a corollary of this, you immediately get that space alone cannot give you Nakamoto-like secure blockchain, because if I have only space, I multiply all of the timed resource with alpha, nothing changes, but it should change by a factor of alpha by the theorem. Okay. Actually, the theorem is more general. We can have many different proofs of work, many different VDFs types, and it generalizes. And maybe this is the last slide I want to show you. So what are now interesting consequences of this theorem? Let's say this is one particular setting. Let's say you want a more decentralized blockchain than Bitcoin. So you want to use 2 types of proof of work. Maybe SHA-256 and maybe some memory hard function. Okay. So here are 3 weight functions that are secure according to a classification. You could take the sum of the 2 weights. So I record both proofs of work, 2 types of proofs of work. I could take the sum, I could take the minimum of both, or I could take the square root of the product. Both of them are secure in the sense that I told you. But if you think about it for a minute, or maybe longer, which one of them is actually a good choice, then you will see if you take the first class, the sum, it's actually terrible, because what will happen is either almost all the resources will go into DW1 or W2, depending on which one is kind of gives you more reward for, if you invest in it. If you take the minimum, then what you will get is that both of them will have equal weight. So there will be the same amount of W1 as W2. Maybe calibrated with some constants, but it will be the same amount. And I think the most interesting is the product. If you take the product of both and then the square root, what will happen is that it will force if you want to maximize the weight, you have to invest the same amount into both types of proofs of work. And this is like a similar mechanism like this automated market makers, because if you invest too much into W1, then it becomes more and more attractive to invest into W2 and actually balancing it out. Okay, so I'm out of time. These are future directions. So if you want to work on this, there are lots of interesting open problems. For example, which of the secure weight functions are actually interesting? From what are decentralization, what I just mentioned before, which may be sustainability, and so on. What are other resources? I just showed you 3. Are there other interesting ones? For example, we don't really know how to include stake in this entire framework because stake is not really a resource. Yeah. And maybe another interesting thing is, I gave you this abstract framework. You actually have to implement it. In particular, for example, if you have a particular weight function, you want this is a mechanism design question. You want the reward function that rewards parties for contributing resources so that given a particular investment, the honest parties will maximize the weight that they can reach. Because the adversary will do this anyway, but you kind of, yeah. So this is not clear how to do this mechanism design question. Okay, so I end here. I will not tell you anything about the other paper. Okay, okay. So this is ISTA, and this is, yeah, thank you.
Thank you so much, Krzysztof.